Hi, my name is Mr. Peck from Ideas Inc. School, and today we will be discussing about electricity part 2. This section will be slightly longer as we will be looking into the practical uses of electricity. First, let's talk about what is an electrical rating. You can find this information printed at the back of most appliances. This rating consists of information regarding the appliance's power and voltage. For example, a light bulb could have a rating of 30 watts and 240 volts. The unit of measurement for power is watts, and this is also known as joules per second. Therefore, if the bulb mentioned earlier has a rating of 30 watts and 240 volts, this means that when the bulb is plugged to an electrical socket that is rated at 240 volts, the bulb will be able to convert 30 joules of electrical energy into other forms of energy every second. The formula is expressed as power being equal to current multiplied by voltage. Thus, P equals I times V. Let's apply this in an example. This example can be found in the notes. Please pause the audio and study the scenario found on the first page. I am using a computer which is rated for 240 volts and it draws a current of 5 amperes. If the computer is in use for 3 hours, how do we calculate the total amount of energy used? By applying the formula P equals I times V. We will be able to calculate the power by taking the current 5 amperes multiplied by the voltage of 240, thus we will obtain a power of 1200 watts. And since 1200 watts is also known as 1200 joules per second, using the computer for 3 hours, or 10,800 seconds, will use up a total of 12,960 kilojoules of energy. Next, we will discuss about how the formula morphs into two different versions when we integrate Ohm's law into the formula for power. The usage of these new versions depends on the type of circuit. If the circuit is a series circuit, we can substitute V equals I times R into the formula P equals I times V to obtain P equals I squared times R. If the circuit is a parallel circuit, we will substitute I equals V divided by R into the same power formula of P equals I times V to obtain P equals V squared divided by R. Well, take a look at the example given in the notes. Please pause the audio and study the example on the page. Let's begin. Recall the second law of series circuit that states that the sum of the potential difference between the resistors will add up to the EMF of the battery. Since the EMF of the battery is 12 volts, voltmeter 1 will have a reading of 12 volts minus 8 volts, amounting to 4 volts. Next, to find the resistance of each bulb, we simply need to apply Ohm's law. Since this is a series circuit, let's recall the first law of series circuits. That law states that the current flowing throughout a series circuit is the same. Therefore, bulb 1's resistance is found by taking the voltage of 8 and dividing it by the circuit current of 2 amperes to obtain a resistance of 4 ohms. While bulb 2's resistance is found by taking the voltage of 4 and dividing it by the same circuit current of 2 amperes to obtain 2 ohms. Finally, let's calculate the power of each bulb. We can apply the new power formula that is specific to a series circuit. To find the power of bulb 1, we will square the current of 2 amperes and multiply it by its resistance of 4 ohms. And to find the power of bulb 2, we will square the same current of 2 amperes and multiply it by its resistance of 2 ohms. If we did the above correctly, bulb 1 and 2's power will be 16 watts and 8 watts respectively. Moving on, we will be discussing about the use and characteristics of a fuse. A fuse is a cylinder with a thin wire passing through it. This thin wire is usually made of an alloy of tin and lead. For safety reasons, a fuse is always connected to the live wire in an electrical plug. Every fuse has a rating printed on it. The rating determines the maximum amount of current that can pass through the fuse without melting the wire inside. The wire's mixture of metals has a low enough melting point that will cause the wire to melt if a current that exceeds the rating passes through. When the wire melts, this will create an open circuit, preventing the surge in current from entering the appliance and damaging it as a result. A suitable fuse rating is about 20 to 30% higher than the current needed to run the appliance. Let's look at the example in the notes. You can quickly pause the audio and refer to the example on the page. Let's begin. Since the computer's power supply is rated at 1000 watts and 240 volts, we can apply the formula P equals I times V. The current can be obtained by taking the power of 1000 watts and dividing it by 240 volts to obtain a current of 4.167 amperes. As a result, a fuse with a rating of 5 amperes is sufficient to protect my computer from surges in current. But why can't we use a fuse with a 10 amperes rating? That is because this fuse can allow a large current, up to 10 amperes flowing through it and to my computer. This large current can cause a short circuit and damage the appliance. In the next part of the chapter, we will be taking a look at the internal parts of an electrical plug. There are two types of plugs, a 3-pin and a 2-pin plug. The difference between both plugs is due to the presence of an earth wire. The 3-pin plug has an earth wire while the 2-pin version does not. And due to the lack of this feature, appliances that utilizes a 2-pin plug has to be double insulated for safety reasons. Now let's unscrew a 3-pin plug and take a look at the wires found within. In the plug, we will find 3 different wires. A live wire is the easiest to spot because it's brown in color and it will always be connected to a fuse. A live wire is also rated at 240 volts and its function is to deliver current from the power supply to the appliance. Next up is the neutral wire. This wire is also easily spotted as it is connected to the live wire. Both wires must be connected to form a closed circuit. As a result, the current found in the live and neutral wire must be equal. A neutral wire is blue in color and is rated at 0 volts. And because the live wire is rated at 240 volts, this causes the current to flow from the live wire to the neutral wire across the potential difference. On to the final wire known as the earth wire. The earth wire has green and yellow stripes. This wire can be singled out easily by looking for the only wire that is connected to the metallic casing of an appliance. The earth wire is rated like the neutral wire at 0 volts. Additionally, it also has a low resistance. These properties are important because when the live wire touches the metal casing, the earth wire will then provide a low resistance pathway to redirect any leak current safely to the earth. If the appliance is working normally, there should be no current flowing through the earth wire. For more information about how the wires are connected, please pause the audio and study the diagrams in the notes. Now let's discuss about an important device found in all households, which is our circuit breaker. In a circuit breaker, there are 3 main components. They are the main switch, the miniature circuit breaker, and the earth leakage circuit breaker. The main switch controls the supply of electricity into the house. On the other hand, the miniature circuit breaker connects specific rooms or area of the house to the power supply. This circuit breaker will trip when a surge in current exceeding a certain value passes through it. This is an advantage over a typical fuse because the circuit breaker can be switched back on again after tripping. Whereas when the wire in the fuse melts, a new fuse needs to be installed in its place for the appliance to work again. Lastly, all the earth wire in the house will pass through the earth leakage circuit breaker. If this breaker detects a current exceeding 30 mA flowing through, it will trip and cause the house to black out. If the earth leakage breaker trips multiple times, this means that somewhere in the house, there's a faulty live wire that is in contact with the metallic case of an appliance. The final part of the chapter involves the calculation of our utility bills. The Public Utility Board charges everyone for every unit of electricity used. This unit is known as kilowatt hour or kWh for short. This means that the unit for power must be in kilowatts and the unit for time must be in hours. To find out how much energy units are used by an appliance, we can take its power multiplied by the duration of use. Now take a look at the example stated in the notes. Please pause the audio to read the question carefully. Let's begin. First, we will convert the power of 1000 watts into kilowatts by dividing it by 1000. That will give us 1 kilowatt. Second, we find the total period of time by taking 3 hours multiplied by 30 days in a month to obtain 90 hours. Therefore, in order to find the amount of energy units, we will take 1 kilowatt multiplied by 90 hours of use to obtain 90 kilowatt hours. Since we are charged 20 cents per unit of kilowatt hour, our monthly bill will amount to $18. Thank you for listening to the end of this audio clip. As a bonus, you will be treated with 2 real-world uses of the power formula. The first scenario is about whether the power station sends out a high current or a high voltage across the power lines to our households. Contrary to popular belief, a high current is not used to deliver the same power to households. In reality, a high voltage is preferred. That is why the signage hanging on the fences that surround generators will warn you of high voltage instead of high current. So why is it this way? Here are a few reasons. Since the power formula states that P equals I times V, in order to achieve the same power, we simply need to take a high voltage multiplied by a low current. The advantage of using a low current is when the current flows through the cables, less electrical energy will be converted and lost as heat. Moreover, since a low current is passing through, the wires do not need to be thick and heavy. Therefore, tall transmission towers do not need to be built to support these cables. Thus, transmitting power using high voltage increases the efficiency and saves costs. The next misconception is about incandescent bulbs. Contrary to popular belief, these bulbs do not have a high resistance. These high-voltage incandescent bulbs actually use low-resistance filaments. The misunderstanding comes from the tungsten bulbs that we are familiar with. Tungsten is a metal that has a high resistance. So why does most high-voltage bulbs have a low resistance instead? Here is the reason why. Since the power formula states that P equals I times V, if we inject Ohm's law into the formula morphs into P equals V squared divided by R. We use this version instead of the other because our households are connected in parallel. The main issue lies with how power is transmitted from the power station. Because of the previous concept discussed earlier, we now know that the power stations transmit the same power using high voltages instead of current. Thus, because our households uses the same high voltage in all of our power outlets, in order to achieve a high power, we will need the high voltage from our electrical sockets to be divided by a small resistance. That is why all our bulbs at home uses filaments with a lower resistance. We have finally come to the end of electricity part 2. Stay tuned to the next audio clip where we will be discussing the effects of electricity, the types of electrical hazards, and the safety precautions that we need to abide by. If you have any doubts, please approach Mr. Peck. Thank you for listening and have a nice day.